Oke, guys, boleh dimulai.
Oke. Assalamualaikum warahmatullahi wabarakatuh, and good night, everyone. And let us introduce ourselves. My name is Dafa Ramadhan Zidane, and
And my name is Aditya Rahmadi Putra Sasono.
My name is Brilliant Panuntun Karim.
today we'll talk about the math behind the magic of physics engines. So, physics engines are everywhere. It's in video games, robotics, simulations, and even AR or VR. And they give us realistic motion, collisions, and interactions, but behind the scenes, it's all just math, specifically numerical methods that approximate real-world physics in real time. Okay, next. So, well, in reality, um, motion is governed by differential equations. Well, unfortunately, most of these equations can't be solved exactly, especially when you add collisions and constraints. So computers break time into small steps, usually one per 60 of a second, and calculate the next position and velocity from the current state. The challenge is balancing accuracy, stability, and speed because simulations must run in real time. Uh, Karim can read the slides.
Am I reading this slide?
Yes.
So for the next points, unveiling the engine, which is how game simulate the reality. To simulate the game physics, we use dynamic object. For example, physics engine tirelessly solve complex equation of motion for every single object in the game world, precisely calculating their behavior frame by frame. This ensures that a failing create or a storyboard move with a believable realism. And the second one is Newton's law or NODA. Motion is fundamentally described by ordinary differential equation or ODA, which are derived directly from the Newton foundational law of motion. This mathematical framework dictates how objects interact with force and develop momentum. And the third one is the key numerical method. To tackle this ODA efficiently, games employ various numerical methods. While a real method offers speed, it can be unstable. Wrong-Gotha method provides greater accuracy, and Velvet integration is particularly popular for its stability in complex simulation. This sophisticated numerical technique are silent architect behind the breathtaking realism and immersive interactive experience found in today's most popular game world. Okay,
The next did it.
Okay, so bringing worlds to life in numerical methods in action. And numerical methods in action, there are a few examples which are projectile motion. And from projectile motion, from the perfect arc of a thrown grenade to the precise flight of an arrow, numerical methods accurately model these projectile motions under various environmental influences. And the next, there is vehicle dynamics, which is, how a vehicle works and how it operates when on the road, how it moves and how it handles. And one of the examples is experience the thrill of realistic acceleration, the grip of friction, and the subtle give of suspension. Numerical methods make vehicle simulations authentic and responsive. And for collision response, and when objects collide, numerical methods calculate their interactions, ensuring realistic bouncing, shattering, and energy transfer, adding visual impact to gameplay. And for the character animation, The characters move through virtual worlds with believable weight and momentum, thanks to algorithms that apply gravity and other forces to create fluid, natural animations.
So, mastering the arc projectile motion. So the fundamental equations governing projectile motions are position equals initial positions plus velocity times time plus 0.5 times acceleration times time squared. While these equations provide a clear model for constant acceleration, real-world scenarios in games introduce variables like air resistance, changing wind conditions, or even dynamic gravitational fields, making direct analytical solutions impractical. The core challenge arises when acceleration is not constant, a common scenario in games where factors like air resistance, wind, or varying gravitational force comes into play. This dynamic element means that the acceleration factor changes over time, complicating direct calculations. The elegant solution is to break down the problem instead of trying to solve the entire trajectory at once. Numerical methods allow us to update the object's position and velocity step by step, adapting to instantaneous changes in acceleration. Karim?
Okay, next is the Euler's method, which is a step-by-step simulation. For the number one, which is to calculate forces, the simulation begins by calculating all active forces on an object, such as gravity pulling it downwards, and drag acting against this motion. These forces determine the object's immediate behavior. The next step is to determine its acceleration. Now, using Newton's second law, which is F equals m times a, the total force is then divided by the object's mass to determine its instantaneous acceleration, which is a equals F divided by m. Now, this value indicates how the object's velocity will change. Now, the next step is to update the velocity, which is the object's new velocity, or F new, is calculated by adding the current acceleration multiplied by the time step, or delta t, to its old velocity. And this predicts the object's speed and direction for the next moment. And lastly, you just update the position. Finally, the object's new position, or p new, is determined by adding its newly calculated velocity multiplied by the time step to its old position. And this moves the object in the game world. Okay, next.
So the art of balance, speed, accuracy, and stability. Well, every explosion, crash, or the satisfying swish of a perfect basketball shot relies on the seamless execution of these underlying numerical methods. Developers constantly navigate a delicate balance. First is speed, the need for real-time calculations, especially for hundreds or thousands of objects simultaneously. The second one is accuracy, ensuring that physics simulations are believable and consistent, avoiding noticeable glitches or floaty behavior. And the third one is stability, preventing numerical errors from accumulating over time, which can lead to objects behaving erratically or flying off screen. Its captivating blend of physics, advanced mathematics, and computer science all converging to construct deeply immersive and believable experiences that define modern gaming. This intricate dance makes game development as much an art as it is a science.
Now, as for the conclusion, the numerical methods are not merely academic concepts confined to scientific research. They are also the bedrock upon which the entire interactive gaming industry stands. Now, their key roles include realistic motion simulation, which crafts believable movement for every object from a tumbling pebble to a soaring dragon, which enhances player immersion, and stable, predictable interaction, which ensures that every collision, jump, and environmental effect behaves consistently and logically, maintaining game integrity. And the next is dynamic interactive environments. Now, this allows the players to manipulate and experience game worlds that react authentically to their actions, fostering deeper engagement. Next. Okay, so that is all from our group. We are sorry that Karim wasn't able to join. He disconnected halfway in this presentation because he had something to do. But that is it all from us. We are sorry if there are any mistakes in wording or pronunciation. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.